Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azizi Aswad bin HISHAM. My meeting number is D18017. Okay, this is our group member for electrical drive. The first member is AMIR AIMAN bin ROZAILANI. The second member is AHMAD WAFI TAQIUDDIN. The third member is AHMAD FATTAHILLAH, and the fourth member is DHIYA BATRISYIA, and the fifth member is me, Muhammad Azizi Aswad bin HISHAM. Okay, next I'm going to explain about the introduction of our project. Okay, most motor nowadays designed to run at constant speed and produce constant output. Okay, the variable speed drive (VSD) is a mechanical device that can regulate speed, rotational force, or output torque. Okay, this system consists of DC motor, speed loop controller (PID), and microcontroller algorithm. Okay, for the project background, this project describes a variable speed drive for a small-scale model given by an experimental design, implementation, and testing unit application. In this project, we design a mixer using variable speed drive to set it to a specific speed. This system consists of DC motor drive, and controller, and we use MATLAB as our simulation application.
Assalamualaikum, my name is BATRISYIA binti ROSMADI. I am going to explain the system of the block diagram. So the first block diagram is we have PID, which is proportional integral derivative. In this block diagram, the fine control and especially overshoot avoidance require the addition of derivative control in DC motor. For the value of power, we set it to the 0.214596, and the value of current is we set it to the 5.26647. And the last is duty cycle, we just set it to 0. So the next part is PWM, which is pulse width modulation. This model is to use control PWM voltage and H-bridge blocks to control a motor. The DC motor block use manufacturer datasheet parameters, which specify the motor as delivering mechanical at no load speed as 195 radian per second when we run it from the 220 volt DC supply. So, to validate the average behavior, we need to change the simulation mode parameter to PWM, and the timer period we set it to the 0.001 second. So next is we have torque load, which is our group only set it to the 20 Newton meter. The next part is DC motor. In the block DC motor, we have another block diagram, which is the first transfer function is 1 over 0.003s plus 0.5, and the second transfer function is 1 over 0.78s plus 0.016. So the last one is we have the block diagram of sensor. In this model, the sensor is to sense the current, position, speed, and the rotation of the motor. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is AHMAD WAFI TAQIUDDIN EUSUD, and today I would like to present the section 3 of our work project, which is the simulation itself, but I will explain about the system design and the software. As you can see in front of us, this is the system design equivalent to the simulation itself. Okay, before I go through the simulation, I will explain first the software that we use. For the software tools used in this particular assignment is the MATLAB Simulate. Why we use the MATLAB Simulate? Because the advantages is can model a nonlinear system which the transfer function cannot do. That is one of our main reason why we use the simulink. Okay, for the system design itself, we technically design for a blender. Okay, in this simulation we have first and foremost the speed reference, which is 195 radian per second. Then we connect it to the, as you can see, 195 radian per second. We will in radian per second. Then connected to the add component, which is the plus and minus one. Then straight away connect to the PID. Okay, PID. So what the value of the PID is? PID, we got this value. For I, we get this value. T, we get this value, and the coefficient, we get this value. It's not get, but we set it up. Okay, from PID controller, we will connect to the PWM. Let's read the parameter. For the period 0.001, and for the sample is 5 exponent negative 5. Then connect to the control voltage, which is the DC voltage. Then connect to the DC machine. This is the DC machine, which is the, as we can see, the biggest component in this circuit. Then a top load of 20 connected to the DC machine, and a DC voltage source of 150 volt connect to the DC machine. And for the last connection, we will connect to the bus bar, which will read speed, top current, field current, and armature current. For speed, we will connect to the gain of 4. We put this 4, then connect to the scope to read the graph, as well as the top, field current, and armature current. We will connect to the scope as well to read the graph. We use separate scope because we want a nice graph between them. Okay, let us run. This is the speed graph, which is the yellow one is the constant, blue one is the gain. Constant of value of 195 radian per second, like I just mentioned before. For the gain is, it will curve like this before it will turn constant, because gain is purposely to generate input by multiplying the inputs. So the graph is really great and good because the time away from the gain speed is very quick, as much as within 0.4 second only, because it will be constant until 2 seconds. For the other graph, which is top load, this is the graph of top load, field current, and armature current. The graph is quite really well because it will turn constant at 0.4 as well as the graph before. Okay, that's all from the simulation and the software. Thank you.
Okay, now for the working principle. Okay, the first step, we just start and go to the transfer function of DC motor, and the next we find the gains of Ki, Kp, and Kd, and after that we introduce gain and the reference point, okay, each block, and we find the error. After that we calculate the control signal by using this formula. Okay, and we apply control signal to the plant. At the same time, it will go to the feedback to the find error, and after that it will finish. Okay, that's all for working principle. Is result and discussion. Okay. Uh, as we know, this figure is present the simulation result of rated speed in radian per second. Okay, and it related to the reference speed in this figure. This reference speed and this is rated speed. Okay, in this figure we can see that that fast response of the PID control system of the system. Okay, the parameter of the PID. Okay, so P we set to 0.214596. Okay, and the value I is 5.26647, and for D value we just set to 0, and this is respond to the step of a closed loop feedback system is control of the PID value. Okay, and so we can see the peak time of the graph is less than 0.4. Okay, less than 0.4, and it will same to the reference speed, rated speed will same to the rated speed. Okay, next, this figure is present the simulation result of graph torque, field current, armature current versus time, and we can see the yellow one is a torque, and the orange one is armature current, and the blue one is field current. Field current is remain 0, uh, and the armature current and the electrical torque, and the peak time of the both this is less than 0.1. Okay, this 0.1. Okay, the peak time is less than 0.1, and it's mean good for the system, for this system. Okay, that's all from me. Thank you.
Okay, for the conclusion, the variable speed drive VSD can be used in kitchen mixer that contain a various kind of load type, including those that demand constant and variable torque. This drive guaranteed to increase the efficiency and excellent in speed regulation. The PID controller, PWM, and the H bridge ensure all of this. The Simulink has the ability to take on initial condition, which is useful in the future. And for the recommendation, in the future, this system should be more simplified and more flexible, and also can be run in more simple application like Plex. That's all from us. Thank you.